Okay, in this section we're going to introduce the structure of the MOS transistor and talk about the symbols that we will be using to represent these in our schematics, and also we're going to start talking about operation of the device in subthreshold or in the weak inversion region. So last time we were looking at a sort of one end of the MOS transistor. We were looking at an area that was about like this area here, where we kind of zoomed in on the gate near the surface and the so-called source region. And now we're looking at sort of a cross-section, a more typical cross-section through a full MOS transistor. And so the idea is that we have the silicon substrate, which is also called the bulk, which in this case is lightly doped p-type. And we have a gate separated from the surface of the silicon through a thin oxide or by a thin oxide. And on either end of the gate we have a heavily doped N+ region, and one of these is called the source and the other one is called the drain. And then off to the side someplace we have a heavily doped P region at the surface through which we make electrical contact to the bulk or to the substrate. This is called a substrate contact or a bulk contact. And this particular transistor will be an NMOS transistor, an N-channel metal oxide semiconductor transistor. And the idea here is that we have the source, which is going to be the source of the charge carriers that carry the current through the channel region up at the surface. And that current is going to be carried by electrons. Okay, so the mobile carriers here in the substrate, underneath the surface and everywhere in the bulk, are holes normally. But when we start to put gate charges on the gate electrode, we push the holes away from the surface here and create a depletion region and create that little notch, that little low spot in the energy right there at the surface, which is the channel region, through which electrons can flow from source to drain. Okay? And so the drain is the region that is where the electrons go. That's why the source is called the source. It's the source of the charge carriers that carry the current in the channel, and the drain is where they go. And so the source would be the analogous terminal in the bipolar transistor to the emitter. Okay, the emitter emits the carriers into the base region, and then they diffuse across to the collector, which collects them. Well, here in the MOSFET, we have the source, which emits carriers into the channel region, and they go to the drain. Okay, so that's basically how this works. Now, in the last segment, we had the bulk contact kind of coming in from behind or from underneath. Here we have it off to the side. Sometimes there is conductive epoxy that connects the semiconducting substrate from the backside to ground, which is typically where the bulk is connected the most negative power supply to maintain a reverse bias between the bulk and the source and drain regions. So these are PN junctions, and if we bring the bulk to a higher potential than the source or the drain, that forward biases these junctions, which normally we have to be reverse biased. Okay, that can cause a bunch of interesting things to happen which we would normally not like to happen. But we typically will have a bulk contact off here to the side, close by to the transistors, to locally control the potential here of the bulk of the MOSFET. So the MOSFET is actually a four-terminal device. There is the source, gate, and drain, but there's also this fourth terminal, which is sometimes called the bulk. Sometimes it's called the back gate. As we shall see, it sort of comes in a way that's sort of in some ways like the gate, and also some ways not like the gate because of these diodes here that exist between the source and the drain and the bulk. But functionally it comes in kind of like a second gate, and so it's called the back gate in some cases. So bulk, substrate, back gate, these are all synonymous terms for the fourth terminal of the MOSFET. So this is what we would typically see from a top-down view. This is a kind of a layout view. When we design integrated circuits, this is kind of the type of view that we often will be working with. And this line here is the line through which we're taking cross-section through the MOSFET here. And so one of the things to note about this structure is that there are two fundamental geometric parameters that a designer has control over. We don't get to choose the junction depths or the thickness of the oxide, but what we do get to choose are the dimensions of the transistor here. So the transistor is really this area that's shown here in the red and green crosshatch. We get to pick this dimension, which is called the length of the transistor, and this dimension, which is called the width of the transistor. So the length of the transistor is the distance that an electron would have to go from the source to the drain, or the minimum distance the electron would have to go from the source to the drain. Obviously, you could take a circuitous path that takes you along a diagonal here, but the minimum length that it would have to go from the source to drain is the length of the channel. And the other dimension is the width. And this geometric set of parameters is what we have control over as integrated circuit designers. The length effectively divides the current, and the width multiplies the current. And so the current in all regions of operation will be proportional to what we call the W/L ratio. So it's proportional to the width and inversely proportional to the length. This W/L ratio, as it's called, or sometimes the aspect ratio or the strength ratio, is a key design parameter for the MOS transistor. If we're working with transistor arrays, that's obviously not something we have direct control over, and they don't even tell us what the W/L ratio of the transistors are usually. But as integrated circuit designers, these two geometric parameters are things that we have control over and things that we will often pick to our advantage in doing designs. So I guess I should say that these blue lines here represent metal wires, typically aluminum for the lower levels of metal contacts. And this red region here is the polysilicon, polycrystalline silicon, and we make these holes in the insulator between the conducting layers to allow us to contact from, let's say, the first metal layer down to the polysilicon, or the first metal layer down to the source drain diffusion regions. One other thing I will mention about the MOSFET, contrasted with the bipolar transistor that we have been talking about, is that you'll notice that the device here is physically symmetric with respect to the source and the drain terminals. Right? So with the collector, there was an asymmetry in the structure, and that had to do with the doping level. The emitter was very heavily doped. That lived inside a base, which was more lightly doped, and then that lived inside a collector, which was even more lightly doped. And so while there was sort of a functional symmetry, because there were two p-n junctions and we could forward bias either one, we could reverse bias either one, the physical structure of the device in terms of the doping levels was optimized so that the device worked in one direction much better than it did in the other direction. Well, with a MOSFET, the structure is symmetric. The source and the drain regions are basically at the same doping level, and usually the device is physically symmetric. We can actually make devices that are asymmetric if we want, by the geometry that we impose on the device. But most devices are more like this, where they are rectangular and they are physically symmetric. So if you reverse the potentials on the source and drain, if you interchange those voltages, the current just basically changes direction. It should be quantitatively the same, and it should work in a similar fashion in both directions. And so there isn't that same sort of asymmetry that we get in the structure. And that's an important thing to keep in mind. So in terms of circuit symbols, these are the types of symbols that people typically will use in schematic representations of complementary MOS, CMOS circuits. On the top row, we have symbols that are commonly used for NMOS transistors. And down in the bottom row here, we have symbols that are commonly used for PMOS transistors. And the symbols in a column here go together. So if we're using this symbol here on the left for an NMOS transistor, we would typically use this symbol with it if we have PMOS transistors in the same schematic. We use this one, then we would typically use this one for PMOS transistors in the same schematic. We don't usually mix and match symbols from different columns. So I want to just spend a couple of minutes here going through some of these symbols. So the MOSFET is a 4-terminal device, and these symbols are 4-terminal symbols here, these here, and these here. So in the first, second, and the fourth columns are 4-terminal symbols. Very often when we're drawing complicated schematics, we don't often draw the 4th terminal. Often that 4th terminal is suppressed. And in the schematics that we will be drawing and working with this semester, we will be following a particular convention. So when we don't show a 4th terminal and resort to a 3-terminal MOSFET, what we're going to do is have a default assumption for that 4th terminal connection. So for an NMOS transistor, that default will be that it's connected to the most negative power supply voltage, which is for us ground. On a single-ended power supply, ground is the most negative power supply voltage, and so that is the bulk connection for most NMOS transistors. And so when you see a 3-terminal NMOS transistor in the context of this class, it will be, by default, the negative power supply. For a PMOS transistor, it will be the positive power supply. So VDD would be the positive power supply in a CMOS circuit, and it would be the default for the PMOS transistor. And again, these most positive and most negative power supply defaults are so that we ensure that our source to bulk and drain to bulk junctions always remain reverse biased. That provides isolation between the different regions or the different terminals of our devices. And so that's one feature of our symbols. So we would like symbols that allow us to suppress the bulk terminal unless we need to explicitly show for a given schematic or a different given context where that bulk terminal is connected. Well, that creates a problem for these two symbols right away, because the only visual distinction between the NMOS and PMOS symbol for these two symbols over here on the left is whether there's an arrow that points away from the channel region toward the bulk, or whether the arrow points from the bulk into the channel region. So these 4-terminal symbols, we really can't suppress the bulk connection at all. It's just not an option. And in practice, I find that this visual distinction is not particularly great. And so when I see a schematic where people are using these sort of 4-terminal MOSFETs with the bulk arrows, I automatically, the first thing I do is to redraw the schematic with symbols that have for me at least, more of a visual distinction between the NMOS and the PMOS transistors. These bulk arrows are, in my opinion, pretty much useless. They are typically used by people who do device physics and are usually concerned with only a single device or maybe a couple of devices and showing device IV characteristics in their work. They're not concerned with schematics that have multiple transistors of both types, and so I would almost never advocate using these symbols here. One of the nice things about them is that they are symmetric with respect to the source and drain terminals, and so that is the one redeeming feature that they have. So the device is physically symmetric, like I just mentioned. And so having a symbol that reflects that symmetry between the source and the drain is really, I think, important. And so that is the only thing I like about this particular pair of symbols, is that they are symmetric with respect to the source and drain terminals. But other than that, they are pretty lousy. So the second group of symbols here, so these go together, 4-terminal and 3-terminal, have source arrows. And these source arrows are very reminiscent of the emitter arrows on the bipolar transistor. And so these symbols are actually commonly used by analog circuit designers who started out life as bipolar circuit designers. And when they started having to design with CMOS, they basically used device symbols that are reminiscent of the bipolar transistor symbols. And so for the NMOS transistor, we have a source arrow where the source arrow points out, kind of like the emitter arrow on the NPN bipolar transistor would point out toward the emitter. And likewise, the PMOS transistor has an arrow that points in to the channel region, much the way the emitter arrow on a PNP transistor would point from the emitter into the base. So these symbols, because they are reminiscent of NPN and PNP transistor symbols, have some familiarity with them. And there isn't some special thing going on with the bulk terminal, so we can suppress the bulk terminal. So that's good. So I think the visual distinction here is a little greater than it is with the bulk arrows because of the familiarity with the bipolar transistor symbols, and we can suppress the bulk arrows or the bulk terminals if we want. So those are a couple of good things about these symbols. The thing I don't like about these symbols is that they are not source drain symmetric, right? There is an arrow on the source that says, hey, I'm the source. And in some circuits, the source is fixed by the way it's connected, so that the source and drain don't interchange roles during the transistor operation. But there are a great many circuits in CMOS where the source and drain actually reverse roles during circuit operation. In certain phases of the operation, the terminal that has the arrow would be serving as the source, and the other terminal would be serving as the drain. But then during other phases of operation, their roles reverse, and so the terminal that's labeled the source is functionally the drain, and the terminal that's labeled the drain by virtue of not having an arrow would be functioning as the source. And so I don't particularly care for these symbols. If you use them, I will maybe look at you funny and furrow my eyebrows at you, but I will not be angry or anything like that. Not that I would be angry if you were to use these. I would just not be super happy about it because I think these symbols, like I said, are pretty useless. So these symbols here are okay, but I don't like the fact that they're not source drain symmetric. These symbols over here are the ones that I prefer and the ones that I'll be using. And these grew up in the context of CMOS digital circuit design. And the convention is that the NMOS transistor does not have a bubble on the gate, but the PMOS transistor does have a bubble on the gate. Okay, so in digital schematics, usually the bubble on an input or an output denotes that an input or output is inverting, so that the output has to go low for the device to turn on. And that's the way in which we're thinking about the bubble here on the gate. For the PMOS transistor, we have to make the gate go low to turn the device on further. Whereas in the NMOS transistor, there is no bubble, and we have to make the gate go up to turn on the device. And so people do use these symbols very commonly for digital VLSI circuit design in CMOS. And they also actually do use these symbols in analog circuit design. So because the visual distinction is on the gate and not on the bulk, we can suppress the bulk terminal if we want, which is nice, especially for digital schematics at the transistor level, where we have lots and lots of devices running around. So suppressing the body connection is very important in simplifying those schematics. So that's a nice feature. It's also nice that these are source drain symmetric. There isn't an arrow on the source that cries out, hey, I'm the source. And so for those reasons, I really do like these symbols. And these are the ones, like I said, that I use, and the ones that I would prefer that you would use. But like I said, if you want to use these, that's fine. Um, please don't use these. It's just useless. If you suppress the bulk terminal, everything looks like an NMOS transistor, and it's very confusing. So don't do that. Anyway, that's enough for my diatribe on symbols. If you want to read more about that, you can check out the MOS transistor handout.